Welcome to the third presentation in Unit 2 entitled The Disappearing Spoon. It says the Milky Way is nothing else but a mass of innumerable stars planted together in clusters. And that was a great idea put forth by Galileo Galilei. So, it says you should be able to describe the law of conservation of mass in both macroscopic and microscopic terms. You should be able to apply the law of conservation of mass to determine the mass of compounds, and you should be able to apply the law of conservation of mass inside a chemical reaction. So, what you should already know from the first lesson cycle, okay, so say 2.1, is that all elements are made of, or all substances are made of elements and combinations of elements. You should also learn in 2.2 that certain things like charge are conserved in a chemical reaction, and you should know from Unit 1 or second grade that mass is measured with a balance in grams. Okay, so what you learn in the lab is that mass is conserved even when it appears to not be. Okay, there are certain circumstances where it looks like mass is not conserved, but regardless, mass is conserved. So all chemical and physical reactions involve the rearrangement of atoms. Matter is rearranged, but the total mass is conserved. Just like we had total charge being conserved, total mass has to be conserved as well. So, conservation of mass. All matter has mass. Mass can be rearranged into different forms, but the total mass of the system must remain unchanged. So, for example, if you had this be 1 and this be 2 and this be 1 and this be 3 and this is 3, when you take those and you put them together to make the plane, the total mass has to be conserved, so the total mass of this thing would be 10 if I did my math right. So 3 plus 3 is 6, plus 1 is 7, plus 1 is 8, plus 2 is 10. So the total mass cannot change, could be because you cannot create mass and you cannot destroy mass, but you can rearrange the mass particles. So mass on a macroscopic scale. On a macroscopic scale, you're looking at what is the reading on a balance, specifically an electronic balance as you do a reaction. Now, a lot of times, whenever you do this, it appears like you have a change in mass. But if you were to seal this thing off and you were to isolate it from its surroundings, you would see that as the chemical reaction occurs, the mass is unchanged. We consider this to be on a macroscopic scale because it's something that we can actually visually see. Mass on a microscopic scale has to do with individual particles, individual atoms, individual molecules, individual compounds. So the mass of each white circle is 1, the mass of each blue circle is 16, because the white circles represent hydrogen, the blue circles represent oxygen. So the total mass on the left is we have 4 blue circles, which gives us 64. We have 2, 4, 6, 8, 10, 12 of the white circles, and 12 times 1 is 12. So our total is going to be 76 on the left. When we see on the other side, though, is you have 1, 2, 3, 4. You still have your 4 hydrogen, or your 4 blue ones, so you have 64. You still have your 12 white, so you're still going to have 76 total mass. The mass is the same because you're not doing anything to the atoms, you're just rearranging the atoms into different forms. So a lot of times it looks like there's missing mass. If you were to take zinc and place it in hydrochloric acid and then measure the mass of the solution, it would appear like the mass is decreasing. And does this prove the law of conservation of mass fails? And the answer is no. There's a reason why it's called the law of conservation of mass. And the reason is that gas has mass. Okay, whenever you do this, it's producing bubbles, and you can see that right here. The bubbles are being produced. Well, those bubbles do have mass. It's producing hydrogen gas. Now, the problem is that hydrogen gas is actually lighter than the air. It's actually less dense than the air, so as a result, the hydrogen gas moves up. Well, when the hydrogen gas moves up and is no longer a part of the solution, the mass of the solution decreases. The overall mass didn't change. It's the fact that we didn't account for the mass of hydrogen. So hydrogen has mass, and the mass of the hydrogen is less than the air, so it pulls the balloon upward. The mass is still there, just in a different form. So when we combine elements into compounds, we look at the mass, and mass is always conserved in chemical reactions. As a result, we can actually use the atomic mass of substances to determine the elemental mass, or excuse me, not the elemental mass. We can use the atomic mass to determine the molecular mass or the mass of a compound moving forward. So, for example, if I want to know what the mass of N2O5 is, all I have to do is take two atoms of nitrogen and multiply it by the atomic mass for each nitrogen because there's two nitrogens. That gives me 28. Or five atoms of oxygen and multiply it by the atomic mass of oxygen, and then I take those two and I add them together. So the atomic mass of dinitrogen pentoxide would be 108 AMU or 108 grams per mole, which is a lot more common for this class. And that's based on the idea of the law of conservation of mass, that if you find the mass of all the individual pieces and then you put the pieces together, the mass is going to be the same. So it says, what does it mean to conserve mass? Does it mean the mass is always recoverable? And the answer is no. If you were to look right here, you have a combustion reaction. You're burning something. You're watching something combust. Well, if you see the smoke right here, that smoke has mass. It's often referred to as soot or something like that. But whenever you combust something, the fact that you have particles leaving means that the mass is going to be less. That doesn't violate the law of conservation of mass. In fact, you're not going to violate the law of conservation of mass. So you need to be able to look and say, what's wrong with this situation that it appears like I've lost mass? There's a big difference between what it appears to be and what is actually happening. So it says, what is the mass of a CO2 molecule? So I have one carbon atom. So I take one carbon and I say every one carbon atom has a mass of 12 AMU. And how did I get that? I looked on the periodic table and I saw that carbon was 12 and there was a 6 on the top. Some people say, well, what it actually says 12.011. Yeah, you could use the whole thing. We tend to use the whole numbers for the most part when we can when we're doing molecular mass, but if you wanted to use 12.011, you're more than welcome to. Next, I have two oxygens, and I would say two oxygens. And each one oxygen, when I look on the periodic table, has a mass of 16, or I guess if you wanted to, you could use 15.9994 AMU. So now, 2 times 16 is 32, 1 times 12 is 12. Add those together, you get 44 AMU, or you could write it as 44 grams per mole if you wanted to. Next, it says, what is the mass of a molecule of sucrose? And you have C2.3H22O11. And so at this point, you would do the exact same procedure that we just did, but you do it on a little bit larger scale. You've got 12 carbons. One carbon is 12 AMU. You would say I have 22 hydrogens. Each hydrogen is 1 AMU. And then you would say I have 11 oxygens, and each one oxygen is 16 AMU. You'd multiply those out, and then you'd add up the total, and when you do, you should get something like 342 grams per mole, or AMU. You could write it either way. Okay, next it says a student pours 2 grams of one solution into 5 grams of another. Student records the total mass to be 6.8 grams. Explain this result accounting for Occam's razor. Now, Occam's razor means that the simplest explanation is most often the correct explanation. So if you look, I have 2 plus 5 grams on one side, and that's 7, and it produces 6.8 grams on the other. Now, if you look, it doesn't appear like there's any sort of bubbles forming. In fact, it looks like there's solids being produced. So it's not likely that it's going to be bubbles that are being produced. What it most likely is in this case is the fact that when you mix these two solutions together, you didn't get all 2 grams of this. Instead, there might have been just a little bit left in the container, okay, that's on the side of the container, so you didn't pour all 2 grams in. As a result, you had less mass because you didn't get all of the mass from the 2 grams in there. So you have to be able to look at a situation and say, okay, what could possibly explain why I have a discrepancy in the mass? Okay, conserving mass in a reaction. So mass is always conserved in a chemical reaction. Using this, you can actually use it to predict what a chemical reaction is going to be. So for example, if you take copper carbonate, which is what this is, and you heat it, you recover copper oxide, which is kind of a greenish, tarnished copper sort of thing. And you can produce what's missing. Like, what else is missing from here? And you know that mass can't be created or destroyed, and you can see that I'm missing two oxygen atoms. Because I'm missing those two oxygen atoms, I could write it as 2O. Of course, that would be incorrect because we know that oxygen doesn't exist as a monatomic atom. Instead, it exists as diatomic, so the answer would be O2. So this principle of conservation of mass is going to be really, really useful throughout this year, and it's really imperative that you have a thorough understanding of it as you move forward. Okay, and you see this right here. Oh, actually, I was missing the carbon as well. So if you look, I didn't account for the carbon, and some of you are probably wondering why. It is actually carbon dioxide that is produced, not just oxygen. Okay, it says, is mass conserved in the reaction as written? Justify your answer. So if you look, we need to start by counting what's on both sides. And you should be able to recognize pretty quick that it's not. And the reason being is I have two hydrogens and I have three hydrogens. So I have an imbalance right away. I have one calcium and I have three calciums. So this thing, mass is not conserved as written. Instead, what this is going to do is this is going to offer me the opportunity to balance my chemical equation to make it justify the conservation of mass, which we'll learn it a little bit later. It says, what can you do to this reaction to make this reaction obey the law of conservation of mass? And so you have to look at this reaction and say, okay, well, why is it violating the law of conservation of mass? I have one oxygen, I have one oxygen. I have one calcium, I have one calcium. I have two lithium, and then once again, I only have one lithium. So if I put a 1 right here, it doesn't work that way. Okay, it's not balanced. But if I were to change this number right here to a 2, and now all of a sudden I have two lithiums, represents a balanced chemical equation, thereby obeying the law of conservation of mass. Okay, it says this PowerPoint is very clear to say that mass is conserved in chemical and physical reactions. When does E equals mc squared apply, and how does that affect conservation? Okay, so some of you may be familiar with the idea of E equals mc squared, but it's basically the idea that mass and energy are the same thing. So if you have a certain amount of mass, okay, that mass has a certain amount of energy. In other words, there's no difference between the two. The c term is just the speed of light, which is a constant. So the question becomes, yes, you can destroy mass, but it's only in a nuclear reaction. Okay, and we're not going to talk really about nuclear reactions in this class, but you can take mass and you can create energy. You can take energy and you can create mass because really they are the same thing. Okay, now that's a little bit beyond the scope of this class, but energy and mass are the same thing. So if they're the same thing, are you really destroying mass when you create energy, or are you just rearranging it?